Okay, first thing we covered in this unit was a review of grade 10 science. Okay, and that would be scalar and vector quantities and V equals D over T. Okay, so simple stuff. Okay, so things to remember, a scalar quantity has only a measured value, whereas a vector quantity has both magnitude and direction. Okay, so your mass is a scalar quantity. Okay, it's 75 kilograms. Okay, but your weight is a vector quantity. Okay, it would be 796 newtons down, okay, or something like that. Okay, so magnitude and direction vector quantities. Okay, magnitude only scalar quantities. The scalar quantities that we went over, okay, in this unit: speed, time, distance. Okay, the vector quantities we went over: velocity, displacement, acceleration. Okay, there are others, but we haven't gone over them yet. In this, we'll go over energy, work, which are scalar, force, which is vector, okay, stuff like that. We'll be starting in Unit 2. I wrote them on here, but we didn't need to know the energy or work. Okay. All right, that first day we also reviewed the use of V equals D over T. Okay, we looked at how it was different depending on whether we were solving for speed, that's this one, okay, is distance divided by time, okay, versus velocity, which is displacement divided by time. Okay, so these are a bit different in that this one can be expanded out to also read final position minus initial position divided by time. Okay, because displacement is your change in position, whereas distance is how far did you go. Okay, regardless of whether or not you came back to the place you started from, okay, your distance is still always going to get bigger and bigger and bigger, whereas displacement, okay, could get bigger or smaller depending on which direction you're going. Okay, ringing a bell? Now, we did a bunch of V equals D over T questions, okay? Not gonna be something I would have a 5-mark question on or anything like that, okay? You have to use V equals D over T as part of projectile motion, part of graphing, stuff like that. That's where it'll be. It's a tool to do something else at this point, not something I'm going to assess on its own, okay? We should probably talk about exam format here first, just so that you understand kind of how this is gonna go. Okay, your unit exam will have multiple choice, numerical response, and written response. Okay, so multiple choice, pretty straightforward. That's the kind of place where I would ask simple recall questions about terminology. Okay, very simple calculations, interpretation of graphs. Okay, could be something like that where you don't have to do a bunch of calculating. It's like, hey, what is this graph showing? A, object is traveling at a constant velocity. B, object is accelerating. C, object is moving backwards at a constant velocity, whatever. D, stuff like that, okay, like interpret a graph. Simple calculations, okay, and then checking your understanding of concepts. So I write a short story and you have to tell me whether that person, is, like who went faster, who went farther, or something like that from a story. Okay? Everybody go through it? All right, so in terms of numerical response, okay, just so that we're kind of clear on how that will work. For numerical response, okay, it'll be like more simple calculations where I'm kind of not giving you a mark for the work just because they're so simple, okay, and then I would have like that block, okay, and the block will have whatever number I choose, okay, of squares, and then below that will be like your your little bubble sheet kind of thing. So you could have a decimal, a 0, a 1, a 2, a 3, a 4, etc. Okay, so if your answer was 1.23, okay, you would fill in the 1 here, the decimal here, the 2 here, and the 3 here. Okay, so you would write the number in the box, and you would fill in the bubbles appropriate to those numbers below. Okay? Everybody with me there? Okay. Then we talked about graphing. Okay, we went over 2 different kinds of graphs. Okay, we went over position versus time graphs, and we went over velocity versus time graphs. Okay, so expect to see both. Okay, we did some that were linear and some that were not. Okay, so you could have a question where you had to use y equals mx plus b. And you could have a question where your graph was irregular and you can't, and you have to do something else with it. Okay, I would expect to see both kinds in the either numerical response, probably the numerical response part of your unit exam. Okay, so position versus time graphs, okay, and then velocity versus time. So I'm just going to erase these graphs and we'll just quickly talk about those 2 types of graphs here. All right, so let's say I've got a position versus time graph here. So I got meters here and I got seconds here, and my graph goes like that. Okay, and I'm given the equation, and it's y equals 2.63 times x plus 5.98. Okay, what is that object doing?
Accelerating.
Position versus time graph.
Moving forward.
Moving forward at
A
a constant velocity, right? Okay, its position is changing by the same amount. In fact, its position is changing by how many meters per second?
5.98.
2.63. Okay, this is the slope of the line, right? And the slope on this graph is telling you how much it goes up for every unit it goes over. That would be meters over seconds. Okay, that's the kind of analysis that we went over and that I would expect you to be able to do on Monday. Okay, slope of this line is going to be how many meters every second. Okay, so that'll be our velocity, positive 2.63 meters per second. This is my initial position, because this is a position versus time graph. So this object started at a position of positive 5.98 meters. Okay. So what I would ask you with that type of graph is exactly the same thing I asked you on your lab, okay, on position versus time graphs. I would ask you to calculate what will the position of the object be after 35 seconds. Okay, so in that situation, I gave you time, which is an x value. I'm asking you to find its position. That's the y value. Plug in and solve. Or, okay, I could say, how long will it take to reach a position of 108 meters? Okay, in that situation, I give you y. I'm asking you to solve for x, because how long is time? Manipulate and solve for x. Okay, all things you were asked to do on that first lab report. Okay, so a good idea would be to look at that first lab report. That is exactly what I will ask on your unit exam. Okay, for a linear graph. Okay, if I choose to put that kind of graph.
I have to go. You
Okay.
should have got
I don't think I did, but
Okay.
okay, just go sign up with Kelly then.
Thank you.
Okay. Now, I could also give you a position versus time graph maybe it looks like this. Okay, so we still got meters here, we've still got seconds here, okay, but now maybe the graph does this. Okay. What is that object doing here?
Going forward.
Going forward. Okay, let's say that since it starts at 0, let's say it goes to 8 meters. Okay, what's its displacement during the first part?
8 meters.
Vector.
8 meters forward.
Forward, positive, okay, either one. Okay, let's say that down here this is -6. Okay, so where this line goes to is -6. Okay, what's it doing in this part right here? It stopped. Its position is not changing there. Okay, what's it doing during this whole part here where the line angles down? Moving backwards at constant velocity, right? Okay, and if I had enough numbers, and I do, well actually I don't. Let's say that this was 2 seconds, 6 seconds, 8 seconds, 9 seconds, 12 seconds. Okay, my displacement during this section here, I go from +8 to -6. Okay, my change in position or my displacement there would be -14 meters. Okay? And since I know that happens between 6 and 9 seconds, I could also calculate the velocity during that section. Agreed? Okay. This line's horizontal. What's the object doing here? Not moving. Here, moving forwards, fast, because the line's really steep, almost vertical. Okay? What's the total displacement of this object?
0.
Yep. How'd you know that?
It went back to the 0 line.
Right. It had no change in position. Its initial position was 0, its final position was 0. What's its total distance traveled? Okay. Here we already said it goes from 0 to 8, so that's 8, doesn't go anywhere here. We already calculated this to be 14, and from here to there is another 6, 28 meters would be our total distance traveled there. Okay. Since we know the total time is 12 seconds, could we also calculate the average speed over the whole trip? We could. That's the V equals D over T. Remember I said, I'm not going to ask a question that's specifically about this, but it's a tool. V equals D over T is a tool, okay, to help you solve for other things. That would be a situation. Okay? These would likely be numerical response kind of questions because they don't involve like, no, I got to write out all my givens and I got to do all this stuff. You're just calculating from the graph. Okay? Ringing a bell? Okay. The other kind of graph, okay, velocity versus time. So okay. Oh, sorry, this is time in seconds. What is that object doing?
Accelerating.
That object is accelerating. Okay, this graph is showing us the velocity of the object. The velocity of the object is clearly increasing from this graph. At what rate?
6.34
6.34
meters per second.
meters per second squared, right? Meters per second. Okay, so meters per second squared. And what was its initial velocity?
12.5.
12.5 meters per second in a forward direction or positive. Okay, ringing a bell? Okay, that's a graphical analysis. Okay, what would I ask there? Same things I would have asked you from the position versus time graph. What will the velocity of the object be after 25 seconds? How long will it take the object to reach a velocity of 55 meters per second forward? Okay, something along those lines. Okay, ringing a bell there? Okay. Another thing I could ask you to do, and I asked you to do this on your lab, okay, your acceleration lab. what is the total displacement of this object? Okay, how do we calculate that?
The area under the line.
Right, okay, I can do the area under the line, that's one way. Okay, which is going to require some geometry. Or I can look at what I have here. If I am understanding what I'm being given here, okay, my initial velocity is positive 12.5 meters per second. My acceleration is 6.34 meters per second squared. And let's say that this graph goes up to 10 seconds, okay? Do I have a formula that can calculate displacement with those numbers? Okay, so there's more than one way to, well, in, you know, somebody else's words, peel a potato. Okay, you could do your geometry and go base times height and do base times height over 2 for that, or you could do this. That's the rectangle. Okay, VI is the height, T is the base, and this is the triangle. Okay. They'll both give you exactly the same answer. One's less work. The second one, less work than the geometry. Okay, ringing a bell? All things I would ask you. Okay, so that's for a linear graph. I could also give you a velocity versus time graph that is irregular. Okay, so something like that. Okay, I could ask you the same things. I could ask you to calculate the total displacement. Here you would have to do geometry. You wouldn't be able to just use that formula because it's not one continuous pattern. Okay, I could ask you to calculate the average velocity, so the total displacement. Once you've done all the areas, divided by the total time. That's a V equals D over T calculation. Okay, things like that. All things we've done, and just kind of reminding you today of what we've done. Okay, questions on the graphs? Okay, then we did acceleration, right? We went over all the new formulas, okay? We used the old formula from Science 10 as well. Expect that there will be a couple of acceleration problems in the written response / numerical response, and that there would also be maybe a simple question or two on acceleration in the multiple choice. Okay. If there is one that involves calculating, it probably wouldn't involve you having to do any algebra, mostly number plugging. Okay. But there could be some questions about the nature of acceleration. What does it mean to accelerate? Acceleration is a change in velocity. Okay, all of that kind of stuff. That would be multiple choice territory. Okay, and obviously the acceleration formulas are all involved in projectile motion, which was the last thing we did. Okay, so being able to figure out what formula to use and manipulate it and all of that stuff. Okay, then the part of the unit that we probably spent the most time on, okay, vector addition. Expect that you will have one tail to head, okay, addition of vectors, okay, vector component addition kind of question in the written response. Okay. Also expect a boat question. Okay, so either a going across or a rowing across question. Okay, if you've forgotten what those are, don't worry, I'm going to go over, once I'm done kind of the outline of the test, I'm going to go over examples of all the stuff we've covered in this unit today. Okay, so you get a little refresher on going across, rowing across, all that stuff. Okay, what they all have in common is we always draw them tail to head. Okay, so in this case here, so this would be a boat, these would be two different boat questions. Okay, green is the direction that the boat is being rowed. Okay, blue is the river current. Red is the result. Okay, so in this situation, the person is rowing diagonally upstream. The current is pushing them back and they end up straight across. This is a going across situation because you're not rowing across in this one. You're rowing upstream, so you go across. This example here, the green arrow, the direction that you're rowing, is pointed straight across. You're rowing across. You never end up across. When you row across, you end up downstream. That's why the angle points this way. Okay? I will end up downstream in a rowing across question. Okay? So the first thing you have to do in any boat question is identify. Am I going across or am I rowing across? Okay? And that's usually pretty straightforward to identify. The question would say, you're rowing a boat directly across the river. It'd say that. Okay? If it says that, that's a rowing across question. Okay? If the question says you want to end up straight across the river, that's a going across question. You can't end up straight across the river by rowing toward that point. Okay? You will always end up downstream. Okay? So being able to identify will be important. Okay? Obviously all vectors are drawn tail to head. In both of these boat questions, I had the rowing and the current drawn tail to head. Okay. Okay, and then projectile motion. We had two types of projectile motion. Okay, horizontally projected, so like a person runs off a cliff, okay, or you throw a ball horizontally, okay, shoot an arrow horizontally, okay. And then we had the angled projectiles, okay, where the object is launched at an angle above the horizontal, or below the horizontal. We did do a few like that as well. There's one of each on your unit exam as written response questions. Okay, so there's one of each type, a projected horizontally and a projected at an angle, and they are both basic. Okay, we were gonna have one more day where I was gonna go over some really complex projectile examples. We didn't get to that. I'm not gonna get to that, and I'm not gonna test any like that. Okay, you are gonna have car drives off a cliff, okay? Or a ball is thrown 30 degrees above the horizontal, okay? Something like that, okay? Ball rolls off the top of a building on a decline 30 degrees below the horizontal, calculate how far it is. Those would be a bit more, their method's not different, the situation requires a little more, not even more work, it's just a situation we didn't get to, and we're not going to get to in the interest of time. Okay, as long as you know the basics of projectile motion, okay, the projectile motion question I would ask on the final won't be any harder than the one I would ask on the unit exam. Okay, I have a philosophy on final exams. What makes final exams difficult is the volume of material on them, not the complexity of the individual questions. Okay, I very rarely put a hard question on a final. Okay, I'll ask kind of basic to moderate questions on a final, but I very rarely go harder than that. Okay, I just need to know, can you still do it? Not, can you still do the hardest question I ever thought of on a final? Okay, a unit exam, yeah, I'll ask some hard ones on there. Okay, but it's fresher in your mind, right? You've just done it, so it's not unfair. Okay. All right, so projectile motion. Okay, now, in regard to multiple choice and numerical response, this is something people don't get for some reason. Okay, you've all used a zip grade form before, right? Okay, you have to fill in the bubbles. The first time through your test, don't shade the bubble in fully. Just make a little mark inside in case you decide later you want to change your answer. okay? And do it in pencil. Pencil. Because otherwise, this is what I see. Okay? First time through, somebody reads the question and they're like, oh yeah, and they're so confident. The answer's totally D. And they shade that thing in, and they don't miss a single spot in it. It's all black, okay? And oh shoot, I didn't read it quite right. No, it's A. And they shade that one in, every bit as dark as D. And then they do this. And then they're like, oh, no. Oh, shoot, I did it again. No, it's actually. Okay. The way zip grade forms get marked is I hold my phone over top of it and the zip grade app looks for what's shaded in. What does zip grade say about this question? Or rather, your answer.
Wrong.
That you're wrong. Even if that one was right. There are 3 right answers, and that's what zip grade says you said. That's wrong. That's wrong. Don't be wrong. Erase anything you write completely. Okay? That's why I always say the first time through, just make a little tiny X in the box. Okay, the first time through. Just do this. Okay? And then when you're fully confident of that answer at the very end, you can shade that puppy in real good. Okay? Are you with me there? Okay. Super important. I am not manually checking the zip grade sheets. Yeah. Okay? I don't have that kind of time. Okay? They are designed to save me time. Manually checking sheets doesn't save me time. Okay? So please make sure you shade in only the answer you absolutely are sure. All right. So, another thing, if you have a written response question, the number in brackets at the end is the point value. Same as the assignments you've done for me. Oh, speaking of assignments, the vector assignment. Anybody have that to hand in to me? It was going to be due on October the 6th. Okay, if you have them done, I'll take them. If you don't have it with you, you don't have it done, let's say I absolutely bare minimum need it tomorrow. It should have already been done. Okay, but if you don't have it done, I want it tomorrow. If you have it done right now, I'll take it. Okay, let's see what we remember here. Here's a horizontally projected projectile question. Okay, this object is projected horizontally at 10 meters per second. Okay, and it is going to hit the ground 25 meters from the base of the cliff. Okay, I want you to calculate for me the height of the cliff. Give you a few minutes, see what we remember here. All right, so our givens are that vertically, and this is the kind of the trick on these questions, is that because it was launched horizontally, it was not moving vertically at time 0. That's why we can say the initial vertical velocity was 0 meters per second. Okay, we obviously know that vertically speaking, it's going to accelerate downwards at 9.81 meters per second squared. We don't know the time, and we're looking for the height of the cliff, which would be the vertical displacement of the object. Horizontally, I know that the object is moving at 10 meters per second, and that it will travel 25 meters. Now, the thing I have to remember here is that horizontally, the object travels at a constant velocity. It does not accelerate. Therefore, since I know the constant or average velocity and the total displacement of the object, I should be able to calculate the time using v equals d over t. Okay? Because the horizontal component of any projectile is a constant velocity, I use v equals d over t for the horizontal part. Okay? So now that I have that, then I can go t equals d over v, 25 meters divided by 10. This is going to take 2.5 seconds. Right? So now I can bring the 2.5 seconds over here. Time is the same for both parts because once it hits the ground, it's not doing either one anymore. Okay? So now that I have the time and these two other things, I can calculate d because d equals vi times t plus 1/2 at squared. Right? You could be using any number of our acceleration formulas in a projectile question. Okay? So that'll be 0 times 2.5, so that'll be 0, okay, plus 1/2 times 9.81 times 2.5 squared. I'm not making 9.81 negative here because the object only ever travels in a downward direction, so there's no need to make it negative. Okay? So I would have 0.5 times 9.81 times 2.5 squared. I didn't even bother to put in 0 times 2.5 because that'll just be 0. Okay. All right, so this cliff to 2 significant digits is 31 meters tall. Okay, or the displacement was 31 meters down. But if the question asks you how high is the cliff is 31 meters high. Okay? Ring a bell? Okay. Just gonna make this a little less busy to start it off with. Okay. Object is launched at 50 meters per second, 30 degrees above the horizontal. Okay. I want to know how far it travels horizontally, assuming the launch point and impact are level. And I want to know the maximum height of the object. This is exactly what I will ask on your unit exam on Monday. I will ask for the total horizontal displacement and the maximum height. Okay, so a couple of reminders, because it's been a while. Okay, this side of the launch triangle, okay, so this launched velocity, that is not the vertical, that is not the horizontal. I use it to get those things. So the vertical component will be the initial vertical velocity. Okay, how fast it's moving upwards at time 0. Okay, the horizontal component will be the constant horizontal velocity. Okay, so a couple of things that you can calculate. Give you a few minutes and see how we do, and then I'll kind of walk through the first couple steps and give you a little bit more. Okay, just go along that way. All right, so first things we got to do is, as we do with all projectile questions, break it up into vertical and horizontal parts. Okay, so my vertical part will be here, okay, and I'll solve for VI by going sine of 30 times 50. So that'll be 25.0 meters per second up, okay, or positive. Since launch and impact are level, what's VF? It would be after it hits. The instant it hits, the same as VI, but negative. Okay, what goes up must come down. So when I throw something up in the air, okay, it goes up and it accelerates at 9.81 meters per second squared down, right? Reaches a velocity of 0 and then falls exactly the same distance back at exactly the same acceleration. It's got to go exactly the same speed when it gets back down to the launch as it did when it was launched. Okay, in again, the perfect physical world. So the real world, that's not the case, but in the perfect physical world, that's what we say. Okay, so this would be negative 25 meters per second, and obviously our acceleration is negative 9.81 meters per second squared. Here, that acceleration does need to be negative because for part of it it's moving up and for part of it it's moving down. Okay, for our horizontal, we've got to calculate the adjacent side, so we would use the cos of 30 times 50. Okay, 43.3 meters per second, and that's constant. Okay, that's what I have right now. What's the most useful thing for me in any projectile question? Even more useful than that. Time, because I can use it on both sides, right? So if I can get to getting time, that will be a big help. Since I have VI, VF, and A, can I get time? Yes, okay, use our good old science 10 formula. VF minus VI, okay, over A, so negative 25 minus 25 over negative 9.81. Okay, so that'll be negative 50 divided by negative 9.81. All right, so this thing is going to be in the air for 5.1 seconds. I'm going to keep all those decimals in my calculator, okay? But now that I have time, now I can bring that over here. Okay. I know how fast the object is moving horizontally. I know how long it moves at that rate for. Can I find how far it goes? Right, now it's just a V equals D over T calculation. D equals V times T. Okay, so our 43.3 times 5.1. So 43.3 times our time. Okay, so it is going to travel. We have two significant digits in this question. 2.2 times 10 to the 2 meters. Okay, that's how far it's going to travel horizontally. Ringing a bell? Okay. The second thing the question wanted was the maximum height of the object. So height is vertical, okay? So all this horizontal stuff, I'm done with that. Okay? I need to go back to my vertical information. Now, there's more than one way to do this. Okay? I just want to calculate the displacement vertically at this point, which is exactly halfway through the flight. And at this point, how fast is the object moving vertically?
0.
Right. Okay. When you're at the top of that or at the peak, okay, vertically speaking, you stop for an instant before falling back down. Okay. So here's where there's more than one way to do this. Okay. I can solve for the height using this formula. Because I have VI, I have A, and I have T. But what do I have to do with my time that I have there? Divided by 2, because this happens halfway through. So I can use this formula provided I use half the time. Okay, so if I do that, it would be 25 times negative 9.81, okay, plus, sorry, not 9.81, times half the time. Let's get that number. Okay, so 2.5 plus 1/2 times negative 9.81 times 2.5 squared. Okay, if we do that calculation, so 25 times that number, okay, plus 0.5 times negative 9.81 times that number again, squared. Okay, then the maximum height, two significant digits, would be 32. Okay, the other way to do this is to use this formula. It doesn't require us to use the time. Okay, we can solve for d. We have to manipulate, so that'll be vf squared minus vi squared over 2a equals d. All right, so now I can plug in my numbers here. That'll be 0 squared minus 25 squared divided by 2 times negative 9.81. So, 25 squared divided by 19.62. Okay, exactly the same number as it should be. Okay. Questions there? I will ask you a question just like that. Okay? Those two things. Anybody need that anymore? Okay, let's do a boat question. Let's Okay, boat is moving directly, is pointed directly across the river and is moving at 10 meters per second. The river current is 3 meters per second. I would like to know two things. I want to know the resultant velocity . Okay, and I want to know how far downstream it will be when it gets to the other side. To help you with that, the river is 1,300 and 50 meters across.
Big river.
It is a big river. It's like the St. Lawrence or something. It's really wide. Okay. Okay, so here's what we have to realize. The first thing they want is the resultant velocity of the boat. That is going to be this. If I was watching from a drone or a helicopter or a plane from above, I would see a boat moving diagonally across the river in this situation. Okay, so this is going to be our resultant velocity. That is, of course, also going to have an angle. Okay? So, if I'm going to get that, that's just a Pythagorean theorem calculation to get the magnitude. So that'll be 3 squared plus 10 squared, square rooted. Okay, so square root of 100 plus 9. Okay, so 10.44 meters per second to get theta. 10 to the minus 1 of opposite over adjacent. And I can do it this way because it did not specify which angle it wanted. If the question had asked from the initial shore, would the way I'm doing it get me the right answer? It would not, because then it would be wanting this angle. Just something to watch for. Okay? So theta will be second 10 of 3 divided by 10. All right, so that angle is going to be 17 degrees to, oh, actually, we only have one sig, but we'll say that. 17 degrees east of north. Okay, so we'd have 10 at 17 degrees east of north. Okay, everybody with me there? All right. Now, the next thing it wants is how far downstream will it go? I know how fast it's moving downstream, but I don't know how long it's moving downstream. Okay? So, is the amount of time it's moving downstream the same as the amount of time it takes it to get across? It is, just like a projectile question, okay? Once I get to the other side, I stop doing both. So they happen at the same time. That means they also happen for the same amount of time. And I have the distance across, and I have the speed across. So I could calculate the time. T equals d over v, so 1,350 meters divided by 10 says it's going to take 135 seconds to get across. Now that I have that number, now it can go along with this. And I can say that d will equal v times t, 3 times 135 seconds. All right, so that means that we will end up, okay, 405 meters. Actually, we messed up the sig digs here because that only had one. Okay, I guess if we only had one sig dig, we'd say 4 times 10 to the 2 meters downstream. Okay. Questions on that one? Okay, so that's a rowing across question. Okay, because we end up downstream. Okay, let's do a vector question. Do I have a good one here? Okay, here's okay, this is an acceleration problem. Let's do that one. Okay, so a ball is thrown upwards at 14 meters per second. Okay, what is its velocity when it is 2 meters above where it was thrown? Okay, so simple acceleration problem, VI is positive 14 meters per second, or 14 meters per second up. Okay, we're looking for its final velocity when its displacement is positive 2.0 meters. Okay, and we also know that because this is vertical, okay, and we can assume it's on Earth, the acceleration would be negative 9.81 meters per second squared. Okay, so I've got VI, VF, A, and D. So that means it'll be this formula, VF squared equals VI squared plus 2AD. Okay, manipulate this for VF, and all we have to do is square root. Okay, of 14 squared plus 2 times negative 9.81 times 2. Okay, so square root of 14 squared plus 2 times negative 9.81 times 2. Okay, so we get 12.5. Actually, we only have 2 significant digits there, so we have 1 significant digit there. So, yeah, again, that should be 2.0. Otherwise, we get 1 times 10 to the 1 meters per second up, which doesn't make much sense. Okay, now, here's something that in this question, your calculator will never calculate for you, but is also a correct answer. Our answer is positive 12.5 meters per second. Correct answer can also be negative 12.5 meters per second. Why? Chuck? Exactly. It will be at that position on the way up and on the way down. So it could definitely be negative 12.5. But you will never get that answer on your calculator with this formula because this involves taking a root. Can you ever get a negative number when you take a root? So it'll never spit that answer out, but it's another possible answer. Okay? Everybody with me on that one? Weird one, but okay. Valid. Okay. Graphing question, position versus time graph. Okay. Calculate for me how long it will take to reach a position of 78 meters. Okay. So if I'm asking you how long something will take, that's time. Time is on which axis? X. So I'm solving for x. Okay, so x will be y minus b over m. Okay, they gave me the y, 78 meters. So I would have 78 minus 3.23, okay, divided by 1.53. 78 minus 3.23, okay, divided by 1.53. Okay, so 48.9, actually we only have 2 significant digits there. No, we have 3. Okay, so 48.9 seconds. Okay, ringing a bell? Everybody okay with that? Okay. Okay, that one we talked about earlier, calculating the area underneath. Okay, so we talked about that already, so we'll skip that one. Okay, if I was going to calculate the total displacement from this one, would it be a lot of geometry?
Yes.
Okay, so I would have to do like, all right, I've got, okay, a triangle and a rectangle, a triangle, this triangle, that triangle, this triangle, that triangle, calculate them all, add them up. Okay, what about the ones that are below? They would be,
Another triangle.
well, they're triangles, yeah, but they would be negative, right? So when I'm adding them all up, I gotta make sure that those are negative if they want displacement. If they want distance, then they're neither positive nor negative, but we treat them like they're positive. Okay, ringing a bell? Okay, if we had irregular position versus time graph, okay, and I wanted to know what the total displacement was, then I would go this position minus this position, and I would have my answer. Okay, if I wanted to calculate the total distance traveled, that's what these numbers are for. Okay, this is 12, this is 28, this is 10, that's 0, that's 4, add them all together. Okay, and we've got it. Everybody with me there? Oh, there was a rowing directly north. Where's that? Jeez. Let's get going like that. And like that. Okay, try that one. That's about as in-depth as that type of boat question might be. Spoiler alert, that we didn't do before. Okay, we did a rowing across. This one says they want to go straight across. Okay.